Hey, if you've ever tinkered with a microcontroller and ended up staring at a blinking LED wondering, what now? Maybe you've built something with an Arduino and thought, how do I actually connect stuff to this thing? We're talking LEDs, lamps, speakers, or even a tiny motor making your cat suspiciously curious. The microcontroller pins are designed to send and receive control signals, but don't expect them to power your fridge. For example, one of the most popular Arduino microcontrollers, at Mega 328P, has an absolute maximum of 40 mA per pin, and only 200 mA for the whole chip. Better not push it. Stick to something like 10 mA per pin, and your microcontroller will thank you. So what can you connect with such limits? A simple indicator LED can usually be connected directly to a pin, especially with a current limiting resistor. It consumes just a few milliamps. Anything bigger, not so much. You might try a relay. I have one with a 5V coil. Looks perfect. But check the datasheet. It wants 40 milliamps. Not quite Arduino friendly. So what do we do? Enter the transistor. A transistor takes a tiny signal and turns it into a stronger one. Exactly what we need. I will show you two main types and how to connect them to a microcontroller: bipolar and field effect. A bipolar transistor has three pins: base, emitter, and collector. Let's try connected one to a 12-volt lamp. To control it, you need two connections, the signal and ground. The load also needs two, input and output, plus and minus, red and black. You can name it as you want, but one wire alone won't do the trick. Since the transistor has three pins, one will serve as a shared connection. There are three ways to hook it up: common base, common emitter, or common collector. We'll use the most common emitter. Imagine the signal source as a battery. Plus goes to the base, minus to the emitter. And the load current flows between the collector connected to the lamp and the emitter connected to minus. I'm using an NPN transistor. PNP works the same, but with reversed polarity. Plus become minus and vice versa. The base emitter junction behaves like a diode. It will consume all current and wants more and more, and the voltage between base and collector won't rise about 0.7 volts, while we want to apply astonishing 5 volts. But no worries, one humble resistor saves the day, dropping that wild voltage down for a safe 0.7 volts. Let's test our circuit. And it works. The lamp draws about 1 amp, controlled by just 4 milliamps through the transistor. Amazing! Now let's see it in real life, because simulations are cool, but sparks are cooler. The lamp is dim because transistor is not fully open. Let's fix it by reducing base resistor value. I'll explain that later in this video. Here it is. Circuit works in reality. In reality, digital output of a microcontroller have two states, high or low. Think of it like connecting a pin to 5 volts or ground. Most microcontrollers can also let it float, where the pin isn't connected to anything, just hanging in the air. This prevents interference when multiple devices share a pin. Without care, the floating base acts like an antenna, picking up electromagnetic noise and triggering random antics. Add another resistor between base and ground to keep the transistor reliably off when no input is present. They are called pull-down resistors. Pull-up resistors work the opposite way. They connect to positive power line and sometimes they're already built into the microcontroller. They can usually be enabled or disabled in software. Check your MCU datasheet. If you think that we reinvented the wheel, you're right. Our setup is standard. There are even digital transistors with built-in resistors. No extra parts need. About resistor choice, I used 1K while the digital transistor used 10K. Which is better? It depends on the transistor current gain, which is the ratio of collector current to base current. For a 1K resistor and 5 volts input, the base current is about 4.3 mA. With a gain of 100, the transistor tries to provide 430 mA to the load. Choose the resistor to ensure the calculated output current exceeds your load's current, so the transistor fully opens. I intentionally increased base resistor value just for experiment. And because current ratio is fixed, both currents are decreased. Here I powered my circuit from a PC USB port. 4.5 volts is supplied, base is 0.8 volts, so it leaves 3.7 volts to resistor. You can calculate desired resistors dividing volts by amps. Next type of transistor is the field effect transistor, or MOSFET, perfect for higher currents with minimal effort. Unlike bipolars, MOSFETs need almost no continuous current to stay on. The gate is isolated, like a capacitor plate. Voltage controls it, not current. Threshold voltage is when it starts to conduct. Logic level MOSFETs work with 5 volts or 3.3 volts and can often be driven directly from a microcontroller. Sometimes you add a resistor to limit gate current spikes, because MOSFET's gate still eats a significant current just to charge up. For stronger high current MOSFETs, you may need near 10 volts at the gate. You can use a small bipolar transistor to supply it. But be aware that it's reverse in polarity of control signal. And now the high level input turns the MOSFET off, and low level turns it on. To switch your MOSFET off, you must discharge the gate. Otherwise, it may stay on even with zero input. MOSFETs have lower voltage drop than bipolars, so efficiency is a bit higher. High-speed switching requires careful resistor choice. Lower resistance charges the gate faster, but draws more current. This can be solved by using a second transistor to discharge the gate, or by a dedicated MOSFET driver. So, in the simulator everything works. Let's build it for real. And finally, the circuit works. Now we can connect something powerful. Thanks for watching. Like, subscribe, and let your ideas spark to life, literally.